to present a speech on membrane distillation.
Yeah, state of
the art of membrane distillation, which again I think takes an important role in a circular treatment chain of the desalination systems.
Is it not here?
It should be there. In the shared folder is. No, no. Before. No.
What's this?
Oh, okay, great. Missing the
Yeah,
that part. Okay.
All right.
I think it's better you to open in the investor because you lose the
You prefer in Google or in PowerPoint? Visualization.
PowerPoint.
PowerPoint? Okay.
Okay.
I didn't rush.
Great.
But
Yeah, I think.
Didn't realize that at first.
Okay.
See it now. It's in the template, there was a mistake in the template anyway. It's fine, it's going fast. Get out of here.
go ahead.
All right. Okay. So state of the art of membrane distillations. Membrane distillation is an evaporative process. It's based on the hydrophobicity of a microporous membrane. So if a vapor pressure difference is established at both sides, between both sides of the membrane, there will be a vapor flux through the membrane, but liquid will be retained. It's very similar to the non-permeable transpirable materials. So we have sweat, liquid sweat. Sweat come out, which is vapor, but rain does not come in. It's a similar principle. The pore size does not need to be as small as in reverse osmosis membranes because it's not doing the selection. Selection is done by the hydrophobicity of the pores. So as long as the pore can keep this liquid meniscus, this interface between liquid and vapor, we are fine. There is therefore a pore size determined by the liquid entry pressure, which is related to the properties of the liquid and the material of the membrane, the size of the pore, and the pressure, the hydraulic pressure. But the hydraulic pressure typically is low. So as long as we don't exceed the hydraulic pressure of about 4, what's 4? 3, 4, then we are fine, and we can have pores that are in the micron size. How to condensate? We have the vapor coming through the membrane, not the liquid, but then we need to condense the vapor. How do we do it? There are different configurations of membrane distillation to achieve that condensation. The most straight one is using a cold permeate in contact with the membrane, so the vapor condenses directly in a cold permeate. This has the problem that there are conductive losses because there is a cold fluid in contact with the membrane. We can separate this condensation surface by including an additional layer here. So we condense the vapor not on the liquid, but on a separate, typically it's a plastic layer. Here we can then use the feed as a coolant because it's not mixed with the permeate, and the permeate is collected at the bottom. But this gap is full of air, and that means that there is a mass transfer resistance of the vapor to reach the condensation. We can stop that, reduce that mass transfer resistance by closing the gap here, and then we leave the permeate inside. So this is liquid, but it's not stagnant, it's not moving. So there are not as many as many heat losses as in this case, and there is no mass transfer resistance. But we can also extract the air from the gap. sucking the air out with a Venturi effect, and that is the so-called vacuum-enhanced air gap membrane distillation configuration, which is the most efficient. An additional strategy is to extract the vapor from the module and condense it outside, either using a sweeping gas. Then we need a sweeping agent to separate the gas from the vapor, or using a vacuum pump that sucks the vapor out to an external condenser. But then you need the electricity consumption of the vapor of the vacuum pump. Okay, at PSA, at Plataforma Solar de Almería, we have experience with practically all available commercial modules using flat sheet membranes. The most important thing when we evaluate membrane distillation is the energy consumption. And that's related to the heat recovery, because you need a lot of heat to evaporate. But then you can get, there is a lot of heat released in the condensation process. So the key thing is to recover that energy. And the typical way to do it is by, as mentioned before, using the feed as a condenser, and then the feed is preheated by the latent heat of condensation. So the latent heat of condensation is turned into sensible heat, as in a multi-stage flash technology. So an example here, we have the feed originally at 20 degrees, then it can be preheated up to 50. We only need to raise up to 80 degrees, which is the maximum operating temperature of membrane distillation. If we have a very long module, then we can have much more preheating. We need much less external energy. We only need to go from 75 to 80 degrees. But then we produce much less because the driving force is reduced. Whereas in this example, we have 30 degrees difference driving force. I mean, the driving force, no, since the module is long, we cannot consider the driving force as 80 minus 60. In reality, 80 minus 50 or 50 minus 20. In this case, it's only 5 degrees driving force, so the production is less. So there is a trade-off between energy efficiency and flux. This internal heat recovery can be done externally by coupling modules in series, but it's the same principle. To avoid this trade-off, we can recover the latent heat of condensation as latent heat of evaporation, as done in multi-effect distillation technologies. So we have several stages. The condensation, this vapor goes through the membrane, condenses here, and passes the heat directly to the feed for evaporation. So it's a multi-effect system with decreasing levels of temperature and pressure. And this is what this, as I mentioned before, this is like multi-effect distillation, and this MEMSys technology using vacuum to move the feed inside created this, what we call the plastic MED systems, which is very equivalent to a multi-effect distillation. Instead of having evaporators, you have membranes. Instead of having condensers, you have the condensation sheets. It's the same principle, recovering the heat as latent heat of evaporation. Now, membrane distillation modules. This is the summary. Spiral wall modules have better thermal efficiency than hollow frame modules and hollow fiber. Than plate and frame modules and hollow fiber modules. I will go into details. We have the plate and frame modules here. You can see that it's hard to guarantee a good countercurrent circulation between the hot side, the cold side, and the hot side. And it's also hard to, that limits the internal heat recovery. And it's also hard to keep them sealed with this configuration. Whereas in spiral wound, it's much easier to keep a tight module and also to guarantee the countercurrent circulation between the hot and the cold side. So we get much better internal heat recovery. So this is commercial modules. Practically all of them nowadays are using spiral wound configuration. But there is a limitation here. If we want to make a large module, then we end up with very long channels. And a 7 meters long channel has a very large pressure losses inside. So you need, the hydraulic resistance is large. So that limits the size of the modules. But there is an innovation here, and it's combining several envelopes in a spiral wound module. This is what they do in reverse osmosis, incidentally. So this is copying the reverse osmosis modules. And by having more channels, you can increase the residence time with the same membrane area and feed flow rate. So you can increase the internal heat recovery as well. So you get more efficient modules. So examples, you can have 7.2 square meters module membranes with only 1.5 meter channels. Whereas before with 10 square meters, you would end up with 7 meter channels. And even if we increase to 24 square meters, you only have 5 meters long channels, so much more efficient. And if instead of 6 channels, you have 12 channels with practically the same membrane area, you can have even shorter channels with the same residence time. So it goes into increasing the internal heat recovery and the energy efficiency. So, okay, I'm going to present a performance analysis of pilot scale modules comparing the flux of permeate with the heat efficiency. Here is the GOR, is the gained output ratio, is in fact a performance ratio. The ratio between the latent heat required to vaporize all the mass of distilled water produced and the rate of heat addition. So in an ideal system, the GOR is 1. All the heat that you give to the system is used to produce permeate. If we have heat recovery, the GOR can be larger because we reuse the heat. The GOR is inversely related to the specific thermal energy consumption. So we can have the GOR linearly here or the specific thermal energy consumption decreased in this way. So on this plot, we have, this is the trade-off. We have systems with large energy efficiency have low flux, system with high flux have low energy efficiency. So this is depicting the trade-off with all the pilot systems that we have evaluated in different configurations. And now we're going to show the effect of extracting the air from the gap. You have a boost in thermal efficiency and a boost in flux. So we are moving from this line to this other. We are increasing considerably the performance. This is for feed salinity 35 grams per liter. If we compare with the vacuum multi-effect membrane distillation, with 4 effects, we are here. Of course, large flux because we are using 4 times. We are using the feed 4 times, but the energy performance, the GOR is less than 4. 4 effects, the maximum GOR would be 4. If we want to reach this high GOR of the previous modules, then we will need at least 14 effects, which is hardly practical. Okay, so we agree that the best modules are the multi-envelope spiral wound modules operating in the vacuum-assisted air gap membrane distillation. We compare between the different configurations of internal configurations of the modules, and we find that the best one is the one with the largest number of envelopes or channels. It's the best reported operating performance in membrane distillation for seawater, with a specific thermal energy consumption of 40 kilowatt-hour per cubic meter, equivalent to a GOR of larger than 16. And the electrical consumption is low because this vacuum, this is only sucking the air from the gap. We don't need a vacuum pump for that, just a Venturi effect. That's the trick. There is not a significant additional electrical consumption. And the recovery ratio is low. But then we can, if we want to increase the recovery ratio, we can recirculate the feed. And yeah, an additional advantage of having more channels is the lower pressure drop. Comparing the module with 6 envelopes and the one with 12, you see the pressure drop is half in the 26 module because the channels are shorter. So then electrical consumption is lower because there is less hydraulic resistance. Okay, so far for seawater desalination. Now, solar thermal membrane distillation for seawater desalination can only compete with PVRO in off-grid small-scale systems, where you have the batteries and that. The real market opportunity for membrane distillation is to work at high salinity because it's much less affected than reverse osmosis. We can see here the maximum feed salinity we can achieve, 246 grams per liter. Of course, there is a decrease in the flux because the vapor pressure decreases with salinity, but it's much less influence than reverse osmosis. And yeah, we find that there is a range of operating conditions because of this decrease of vapor pressure that we cannot operate. We need to increase the feed flow rate and the temperature to operate. But yeah, we still can operate with 250 grams per liter feed. And the specific thermal energy consumption also increases with salinity. We can see it here better. So this is for 35 grams per liter. As we increase the feed salinity, we move along this. This is for 70 grams per liter. And there is an interesting, not only the decrease of flux and specific thermal energy consumption, but a change in the trend. You can see here that the point that operating conditions that give us the maximum flux are the same that give us the maximum energy efficiency. So there is not this trade-off of maximum flux, minimum energy efficiency, maximum energy efficiency, minimum flux. We find that there is a change in the optimal feed flow rate because, okay, this is for the same module, changing the feed flow rate. Low feed flow rate means large residence time, so high energy efficiency. Large feed flow rate is less energy efficiency because it's less residence time. So we can find an optimal feed flow rate corresponding to the different salinities for minimum specific thermal energy consumption. This is very important because it gives us the operating conditions along the variation in feed salinity that we are going to face when we operate in brine concentration, which is, as I said before, the market niche for membrane distillation. This is what happens with the flux. As we increase the time, we are recirculating the flux, operating in batch mode. Then we are recirculating the feed flow rate, the feed, we decrease the flux as salinity increases. And in relation to that, the specific thermal energy consumption increases. But we need to look at the integration, the integral between, if we operate for 4.5 hours to reach 223 grams per liter with a feed salinity of 70, then the total specific thermal energy consumption is the integral here. So in 4.5 hours, we can reach 70% recovery from reverse osmosis brine, concentrating up to 223 grams per liter with a specific thermal energy consumption of about 180 kilowatt hour per cubic meter. This kilowatt hour is thermal energy, not confused with electrical energy, which is much higher exergy and much more expensive. This is cheap, low temperature thermal energy. And something else, well, this is to illustrate the specific energy consumption of the process. It's less than 0.5 kilowatt hour per cubic meter, but also that the next steps in brine concentration, where are we? We want to demonstrate it in the Sol2 project using real RO brine. This has been introduced before. We have also a project. There is at the University of Almeria to do something similar, but without the pre-treatment of the RO brine and in a larger scale. And coupling with solar energy. This is another aspect that we're going to demonstrate at EBORAC. And the key thing here is that solar energy is variable. So that means that the feed temperature is going to change along the day. We need to see how the performance of the system changes with that. And when you have this situation, storage is critical. So we use heat storage. And this allows us to reach the desired temperature. We can store the excess heat here to have a more constant operation along the day at the given temperature. But still is something that we need to consider. Here, the dimension of the solar field is very important. And the set point. And so we have an example here of a unit of 6.4 square meters size and a solar field of 17 kilowatt thermal with a storage of 1.5 cubic meters. To keep a set point of 60 degrees, we have no problem. If we set the point at 70 degrees, then we are about 15% of the operating hours below 60 degrees. We cannot reach this set point. And if we want to operate at the maximum set point, we find that very hardly we can reach it. Most of the operating hours, we are quite below that set point. So that's something we need to consider. If the unit is more efficient, then the solar field is better dimensioned, then we can increase the number of the amount of time that we can operate at the desired set point. But this is something that we need to take into account. Sizing of the solar field is critical because that's where the CapEx goes in the solar collectors, but also changing the operation, changing the temperature of operation to maximize the use of heat. And what we need to use in this case is artificial intelligence techniques that adapt to the variability of the energy source. Oh, do I have?
Yeah.
All right.
Maybe just.
So to wrap up and go, this is the state of the art. This is what we want to do. Let's go a bit further than that. So we have operating in brine, in recirculation, in batch mode. We have this, the feed enters here, then the brine, this is the heat is preheated, then it's evaporated. We have the brine, we recirculate the brine, so we need to dissipate the excess heat that the brine might have. We can use the seawater as coolant. With a large feed flow rate, then we dissipate that heat. But there is an opportunity to couple this with a heat pump to supply heat and cooling at the same time. That's a very interesting combination that is there at the forefront of the state of the art. We are working on this right now with the University of South California. And there is also the electrolysis coupled with membrane distillation for green hydrogen generation. If you look at electrolyzers, PMs have waste heat that needs to be dissipated. The waste heat is at about 80 degrees, which matches perfectly the heat source for membrane distillation. And membrane distillation produces water with very good quality because it's evaporated and condensed, unlike reverse osmosis that has filtered. So we have very low conductivity that fits the electrolyzer. So we don't need a cooling system in the electrolyzer. Pure water is produced at zero cost using the waste heat. And then we can move this wherever we have salt water. We don't need the availability of fresh water. So that's also something that is being researched nowadays, and this is something that we are doing. This is it.
Okay.
If you have.
We are a little bit short on time, but anyway, maybe one question. Please.
Maybe you saw it with the numbers for electricity consumption.
Of the, yeah.
You need to operate the module beyond the thermal requirement, thermal energy requirement, also the electrical consumptions.
As a specific electrical consumption. Keep in mind that it's just a pump circulating the water through the module. The vacuum is not really vacuum, it's sucking with a Venturi effect. It's practically okay. There's an additional hydraulic resistance, but not much.
So it's really a minor contribution. Okay, thank you so much. We switch then. We have to further proceed with the next presenter, Isabel Oller from Plataforma Solar de Almería, and she will present on solar water treatment, integration of technologies for wastewater regeneration.